So welcome to Chemistry 111. Today we'll be starting Chapter 3. Shouldn't be a whole lot of math in Chapter 3, but may get into a little bit near the end. But the first part will be all about kind of naming. So we'll look at that in just a second. So we're going to get into how do we name compounds, and then what is a mole, and how do we calculate it. So this one's a little different setup depending on what book you have, but the general gist of it is you get the basics of, we learned what makes up an element in an atom. Now we're talking about what makes up compounds before we can start to do any chemistry. So we need to be on the same page when it comes to naming everything. And how do we deal with these things, which will thoroughly involve Chapter 2, Lab 2, when we eventually get there. Okay. First thing is, remember, chemical formulas. That's where we're going to start with. The major focus of the chapter is called chemical nomenclature, which is basically the systematic approach to naming compounds. As tough as this may be, it's no organic chemistry, which is far more in depth when it comes to chemical nomenclature. A lot more rules there. But we'll take turn in turning what we call chemical formulas into names and names into chemical formulas. So how, by looking at the name, do I know how do these get mixed apart? Or looking at how these two elements are mixed together, or three elements mixed together, how do we go about naming these? But first things first, a chemical formula, remember, is made up of the atoms in what we call the formula, the quantities of each element in a compound represented by its subscripts. CO2 says for every one carbon, there's 2 oxygens. NaCl says for every 1 sodium, there has to be 1 chloride. Now, we're going to break these mostly into 2 different types of compounds. And the first thing we need to be able to do is recognize and classify these, because the sooner we can recognize and classify these, the easier it is going to be to name these. There's typically 2 compounds that are both nonmetals. They're bonded through a sharing of electrons called a covalent bond to form a defined structure, which we call a molecule. They will be a classic compound called molecular compounds. Typically speaking, it's like from carbon on to the right. Anytime we have a mixture of carbon or anything on the right quadrant of the periodic table where it's a nonmetal bound to another nonmetal is going to be named through this type of molecular compound, because we can define this as a individually defined compound. If I say CCl4, I know there's exactly 1 carbon and 4 chlorines. Full stop. That is a whole molecule by itself. The other class will be what we call ionic compounds. It was when we mix a metal with a nonmetal. So the left majority of the table mixed with the right quadrant of the table. Now, when these guys mix together, they form a repeating 3D lattice structure. Basically, a repeating 3D pattern of NaCl, 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 left, right, up, down, front, back, to make up a crystal. Now, these exist via electrostatic interactions between an ion. So we have positives and negatives kind of woven together like a quilt. And because of it, it's not just one defined little quilt square. It's thousands of quilt squares. So we cannot define this into a single molecule like we can with the molecular compounds. It's going to be thousands of NAs, but there's also thousands of CLs. So we will represent this as the simplest reproducible formula unit. And when we call that an ionic compound. So when I say NaCl, we're saying there's just one Na per one Cl. If I say CaCl2, I'm saying in this crystal structure, for every one calcium, there is 2 chlorides. Sure, there may be a billion calciums, but that means there's going to be 2 billion chlorides in there. And we can simplify that down to a 1-to-2 ratio. So they're going to be named in a similar fashion, but in the long run, it's going to be very different. So we need to be able to recognize this is a metal, this is a nonmetal, so it's going to be named like this. This is a nonmetal, and that is a nonmetal, so they're going to be named like that. And that will help us when we go to turn a formula into a name. Now, there's a few diatomic elements. Certain nonmetals will form molecules in their pure elemental form, and this is to stabilize the electron count. We will need to learn these, memorize these, and just recognize these. So hydrogen gas is not just H, but H2. So whenever I say hydrogen gas, or elemental hydrogen, I'm referring to H2. The same thing with nitrogen gas, it's N2. Oxygen is O2. Basically, hydrogen, and then you go NOF across the top table, and then from F down, F, Cl, Br, and I. So if I'm looking at the periodic table, which there is one in the room, but you look, hydrogen is number 1, and then you have nitrogen, which is element 7, oxygen is 8, fluorine is 9, and then you're moving down from fluorine. Fluorine, chlorine, bromine, iodine. All of those are diatomic. So whenever I say iodine, if I use some iodine, I'm meaning I2. So we will assume these guys are diatomic unless I say something like this is an anion or monoatomic. Breaking that down, monoatomic means one atom. You can have monoatomic hydrogen. You have a bunch of that when you do some solar fusion. But we're not in the sun right now, so we're not going to have to worry about that. So let's start with molecular compounds. These guys are pretty short, pretty easy to deal with. There's not a whole lot of exceptions here. We can just name them like this, so we're going to knock these out of the way first. Mainly when we deal with molecular compounds, we're going to be dealing mostly with binary molecular compounds. Binary means 2 nonmetals. Whenever we have 2 nonmetals, we're going to combine these guys together. One guy is going to be treated like a cation. One of these guys will be treated like an anion. And I realize I haven't talked about how we treat an anion yet, and that'll come up again in the next slide or two. So the problem with these molecular compounds is they could be mixed together in a variety of different ways. Because they can be mixed together in a variety of different ways, we need some way to designate the different ways they're mixed together. Just take carbon and oxygen, for example. We all know CO2. That's something we exhale every time we breathe. We all kind of know a little bit about CO, carbon monoxide. That's a thing, one of a byproduct of incomplete combustion. You start like a hibachi grill in your dorm. That's why they say not to do that, because you could be producing carbon monoxide. You breathe too much of that in, you pass out, you die. We look at different types of nitrogen and oxygen. There's NO, there's NO2, there's NO3, there's N2O, there's N2O4. There might even be some more, I don't remember. But there's a lot of different ways you can combine nitrogen and oxygen together that are valid compounds. So how do we designate these guys apart? So we're going to use these prefixes. The prefixes are going to state how many of each element is present. So mono means one. Like monotone voice would be a voice that's one is unchanging. Di means two. Tri, you remember tricycle, that means three. Tetra is our four. Penta, like a pentagon, is five. Hexa is six. Then we get into some weird ones. Hepta is seven. Octa is eight. Nona is nine. And deca is 10. And you could keep going, but we're probably not going to see 11 and 12 very often. So we're going to leave those off. Now we're going to use these prefixes in front of most of the atoms in the formula. One of the exceptions, though, is if the first element is mono, we leave it off. We're going to assume the first element is one unless we say otherwise. So CO2 is not monocarbon dioxide. It's just we say carbon dioxide. We're going to assume carbon is one unless it needs to be otherwise. Carbon monoxide is one carbon, one oxygen. Nitrogen trioxide would be one nitrogen, three oxygen. But if I'm saying dinitrogen monoxide, that would be two nitrogens, one oxygen. So I'm using the prefixes on the second one always, but the first one only gets a prefix if it's not one. One of these guys, the first guy in the chemical formula, will just be given its name. The second one in the chemical formula will be given an ending like an anion, which is when we give it an IDE ending. Fluorine is a neutral compound. Fluoride is the anion. I've changed the INE to IDE. And I'm treating it like it's charged. Sulfur is a neutral compound. Sulfide would be the charged version. Oxygen is the neutral compound. Oxide is the charged. So we're going to change the second one's ending. Now, typically when we name these guys, we're going to be reading from left to right in a row, bottom to top in the column. But typically speaking, if you read this, the formula, you can just read left to right on the formula. The first one gets the name. The second one gets the special ending. And when you're reading a name and turning it into a formula, the first element goes first, the second one goes second. Because otherwise the exception, the exception is halogens take precedence over oxygen. Basically saying that it's not oxygen, dioxygen monochloride, it's chlorine dioxide. But that shouldn't ever have an issue, because when we ever say, if I was to give you chlorine dioxide, I would write ClO2. So I'm just reading, well, chlorine comes first, oxygen comes second. And if you're expected to draw ClO2, if you're expected to draw ClO2, you're expected to draw ClO2, I would be telling you it's chlorine dioxide. I wouldn't be switching it around. So whenever I'm reading a formula, I can always read from left to right. Always read from left to right. So if I'm giving you N2O4, I can read, so that's nitrogen first. There's two nitrogens, so I say dinitrogen. There's four oxygens, tetra oxide. So I'm reading it from left to right. Chlorine dioxide. So like, oh, I'd give you SO2. That would be sulfur dioxide. So you don't have to worry which one comes first. Well, I'm reading from left to right. Left to right. As I said, the second element is always given the suffix IDE. Nitrogen NF3 is nitrogen trifluoride. P2S3 is diphosphorus trisulfide. Now, when we get to hydrogen, hydrogen is technically a nonmetal. However, hydrogen acts differently. It typically acts like an acid, and so we'll name this differently. And even when it's not an acid, it will still typically have a weirder name. So NH3, instead of being nitrogen trihydride, is ammonia, which is a common name that we see. And phosphorus trihydride is phosphine, not, as I said. So hydrogen is the exception. So typically we're looking at just compounds in the right quadrant of the table. They're all nonmetals, but I'm saying hydrogen acts differently. Hydrogen always acts differently. It screws up the name. So we're not going to name those guys like a molecular compound if it has hydrogen. We will get to those acids later. But first, we need to learn about ionic compounds. Okay. So just some quick practice. So we got to remember our naming scheme. First, you have to recognize the elements on the periodic table. This might take a little bit of time. That's fine. Most of the tables you can have will have names on them, so you don't have to, if you don't get them right away, that's fine. But silicon, there's 4 bromine, so tetrabromide. We did carbon dioxide. H2O is technically water, but if you were to try to name it the same way we've been naming it, it would be dihydrogen monoxide. The joke is that there's often been many different petitions passed around trying to ban dihydrogen monoxide, believing that anyone will sign on if you make it sound scary enough. Like dihydrogen monoxide is in nuclear reactors, it's in our streams, it's in our rivers, it's responsible for so many deaths a year, it's in a lot of our vegetables, it's making up a good percentage of celery, it's found in our bodies, and we can't really have trouble getting it out. You know, you can make dihydrogen monoxide sound incredibly scary without really stopping and breaking down. Oh, dihydrogen, that's 2 H's and 1 O. You can't ban water. It's not really good. SO3, so sulfur, we got the trioxide. AS is arsenic, so diarsenic pentoxide. 5 oxygens. This one's a little weirder. Tellurium, 6 of them, hexachloride. Hexachloride. Antimony, another weird one. Mononitride. Just dinitrogen triselenide. And carbon monoxide. Come on. So if you don't write them down, that's fine. They're on the slides. You should have access to the slides. If you're having trouble getting access to the slides for whatever reason, let me know. I'll get you access to them. But they should be on the Google. So as I said, you don't need to write those examples down. So naming ionic compounds. Ionic compounds, we are going to try to make a neutral compound by mixing a cation, which is the positive charge, and the anion. The net goal is the total number of positive and the total number negative should add up to get a net zero charge. If you do not have a net zero charge, you still have a charged compound, and it's not a true ionic compound. These ionic compounds are our salts. For a salt to be a solid, a salt be something we can deal with, it needs to be balanced. It needs to be balanced. Now, the simplest whole number ratio of cation to anion is our formula unit. Now, we are going to name some of these based on the group. Group 1, Group 2, and Group 3 are going to have a simple way to name them. The transition metals are going to have a separate way to name them because of trickiness. So Group 1, if you look at the periodic table, Group 1 is column 1. It's our lithium, our sodium, our potassium, our rubidium, our cesium. Group 2 is the second column, beryllium, magnesium, calcium, strontium, selenium. Group 3, we jump to right below boron. So group 3 is, for all intents and purposes, just aluminum. But the idea here is what we'll learn a little bit later is the charge of the cation will be equal to the group number. There's a reason behind this, and we'll learn this in the next chapter or so. But the reason behind this, the charge of the cation is equal to the group number. So group 1 are all +1. Group 2 are always +2. Aluminum, if it's in a compound, is always +3. No matter what compound they make, they will always be +3. So for that reason, we don't need to know anything more. If I say aluminum chloride, I know it's +3 aluminum, and chlorine will have to be -1. And so there's always going to be 1 aluminum, 3 chlorides. So I don't have to reference the name. So when I say sodium chloride, because I know chlorine is -1, and we'll get to that in a minute, and sodium is +1, they have to be mixed together in a 1-to-1 ratio. When I say potassium carbonate, we haven't learned carbonate yet. Don't worry about that, but carbonate is 2-. Because I know carbonate is 2- and potassium is 1+, I have to mix 2 positives to cancel 2 negatives. And so I'm going to mix together 2 with 1. 2 +1s with 1 - 2. And they cancel out to give us 0. 1 + 1 - 2 is 0. So I don't have to reference anything about a number. Not like we did with our molecular compounds. There's no reference to a number. I just can say potassium carbonate, and anyone who knows about potassium and carbonate knows, oh, I know exactly how many are mixed together. Same thing with sodium oxide. If you know oxygen is 2-, you must mix together 1 2- with 2 +1s. Sodium peroxide, peroxide is O2 2-. It's a weird one. We'll learn about that later, but the same way, we mix together 2 +1s to cancel 1 - 2. Now, if we're just naming a single ion by itself, you can single ions, the positive ions of a metal with 1 stable charge will just be given its name. All these guys, I said 1A, 2A, 3A, those guys have a stable charge. So when I just say aluminum and I want it charged, I can just say aluminum ion. I don't have to do anything fancy. I just say aluminum ion. But there's also a few stable transition metals. These guys you kind of have to memorize. The only ones that will really come up are zinc and silver. Zinc and silver are the 2 ones that will show up with some regularity. Zinc is always 2 plus. Silver is always +1. I think cadmium is another one, but we rarely use cadmium. At least I rarely use cadmium as a name, I promise. When I say zinc, I can just say zinc ion because zinc is always +2. Silver is always +1. Quick reminder, when we take the anions, we'll take the base element name and replace it with an IDE. Oxygen is oxide, chlorine is chloride, sulfur is sulfide. It's one of those things, some of them, the rule of the suffix is a little bit hard because it kind of changes. We don't say sulfuride. We take the UR off of sulfur and take the IDE. Phosphorus, we take the orus off and change it to ide, so it becomes phosphide. The nitrogen, we take the ogen off and it becomes nitride. So how these suffix changes, it's not always consistent because all the elements have all sorts of weird names. Carbon becomes carbide. Chlorine, fluorine, bromine, and iodine all have the same changes. Selenium becomes selenide. It's just a matter of kind of learning them a bit. But so like oxygen and nitrogen lose the ogens. And so BaCl2 is barium chloride. ZNO is zinc oxide. We don't have to use any sort of descriptor other than just the name. Because of only one charge means we don't have to specify. Once you learn the charges and you learn the basic names, you know how they go together and how they cancel out. Now, before we get too far, this is how we learn the charges on most of these guys. Elements will like to be like a noble gas. A quick reminder, a noble gas is this 8A column, this 18 column right here, the periodic table. Helium, neon, argon, krypton, xenon, so on. All those are noble gases. Every element will want to be like them. They want to have a similar electron count. We will talk more about this in the following chapters. But so they will want to either gain or lose electrons to get to be 18. So if you're in group 1, I could either gain 7 electrons to move all the way over here to 18, or if I lose 1 electron, I start over at the back. So if I lose 1 electron, I move to the left. If I move to the left, it circles around. So lithium becomes like helium when it loses 1 electron. When beryllium loses 2 electrons, 1, 2, it becomes like helium. So beryllium only wants to lose 2 electrons because it's easier to move 2 to the left than it is to move 6 to the right. So all of these guys are, in the first column, are 1 element away from the corresponding noble gas. So everyone in column 1 will want to lose 1 electron. Everyone in column 2 are 2 elements away from the corresponding noble gas. So they'll only want to lose 2. Aluminum, aluminum right over here. I know we have this big gap, but going in proper order, 1 electron puts it at magnesium. 2 electrons puts it at sodium. 3 electrons puts it at neon. So aluminum is 3 plus. Now, looking at these common these common nonmetals. This guy on group 5A or 15, I could move 5 electrons to the left to get like neon. However, I could move 3 electrons to the right and get to be like neon. Which is closer? 5 left or 3 right? Say 3 right is far closer, so we would prefer to gain 3 electrons. Same thing, phosphorus, 3 to the right. It's in group 5, it takes 3 to get to 8. Oxygen, sulfur, selenium, they're on group 6. They take 2 electrons to move it to group 8. Fluorine, chlorine, bromine, and iodine, 1 electron to move to group 8. So they'd much rather gain 1 electron than lose 7. All that coming there. Now these transition metals, you'll notice some of these transition metals have 2 charges. Some of them even have 3 charges. So we're going to have to name these guys differently, because if they have more than 1 possible charge, there's more than 1 possible combination between metal and nonmetal. And so it's a little bit harder to predict. But for all intents and purposes, we're going to add these guys together so that they're neutral. So using this little thing. Now carbon. Carbon is one of those wishy-washy ones. Carbon is group 4A. It's not on here, but what's one of the possible charges of carbon? How many elements does it have to move to get to a noble gas? Anyone? To get to a noble gas of 18 or 8, how many places does it have to move? 4. Now we can move 4 to the right. 1, 2, 3, 4. But you notice it could also move 4 to the left. 1, 2, 3, 4. And if you try to predict it based on what it's bound with, it can be equally likely to be either one. If it's carbon dioxide, you could treat it like 4 plus, and oxygen each 2 minus. 2 oxygens at 2 minus is -4. Carbon at +4 cancels out. But CH4, methane gas, would be carbon being -4, and we have 4 hydrogens each at +1. So depending on what we have bound to it, it could be either plus or -4. It's kind of the place where it could be either or. You'll notice hydrogen could also be either or. It could gain 1 electron and be like a noble gas, helium. But it could also lose 1 electron and be at 0 electrons. So depending on what it's bound to, it can either be plus or minus. Typically, it's only minus when mixed with, say, lithium or like another metal. Now, transition metals. To name these transition metals, when we name a transition metal and we know its charge, we can read off its charge. We are going to state the charge in the name. We're going to state it as a Roman numeral, but when we say it, it's just going to be that number. So Fe2 plus is iron 2 ion. If I have Fe3 plus, would say iron 3. Please note, there is not a number for every atom. There's not, like, for example, there's not an iron 1. There's not an iron 4. We jump straight from iron 2 and iron 3. The number refers to the charge, not to a set of series. So in order to determine the charge of a cation, we're going to look to the, if they are mixed together with something else, we have to use the anion to help us. If it's not just obvious, we'll have to use the anion to solve the quandary. So just looking at this, Cu1 and Cu2 is copper 1 and copper 2. I'm going to skip mercury for now because mercury is a tricky one. Sn is tin. We have tin 2 and tin 4. There is not a tin 3. There is not a tin 1. You're not going to see those. If they exist, they are not really stable. Now, mercury, the one on the right is obviously mercury 2. But what about this guy? This guy is also 2+. But you'll notice it's a diatomic. It means there's 2 mercuries. And so that 2+ is actually split apart between the 2 mercuries. So 2 divided 2 is 1. So we call that mercury 1 and mercury 2. Mercury is a really weird metal. Really, really weird. Mercury 1 and mercury 2. Now there is a like a Greek name to name these guys, but it don't really need to worry about it. But like where we add an OUS or an IC ending to tell you the difference between this, you could have ferrous and ferric, cuprous and cupric, stannous and stannic, but we're not worrying about that. It's beyond what we're going to deal with. But if you ever look up on Google FeCl like 3, they might be saying, oh, that's ferrous chloride or ferric chloride. They're referring to, yeah, I think FeCl3 is ferric chloride, and so it's like one of the names. But that's just the old way of naming with and stating the charge. We're going to go with the easy way. But actually, I'm going to take a quick break to give a couple examples of this. So before we go into some of the harder stuff, this is not on the slide. So in situations where we do not have the ion directly stated, we have to look to the anion. So if I said FeO, I have to look what is the charge of oxygen to find out what is the charge of iron. It's obviously a iron, but is it iron 2 or iron 3 oxide? In a case like this, we know the oxide, but what is the iron? Well, we have to look. Oxygen is group 6. Group 6 likes to move 2 to the right to get to group 8. If that's 2 to the right, this would have to be -2. If that is -2, this would have to be +2. So this is going to be iron 2 oxide. We'd name it iron 2 oxide. I used the oxygen to help me there. Use the oxygen to help me. If I said this is Cu2S, once again, copper could be copper 1 or copper 2. We don't necessarily know. So we have to look sulfide. I know this is a copper, but what copper is it? Sulfur, right below oxygen. If oxygen was -2, then sulfur is -2. There's 2 coppers. So copper, in order to give us a charge of 0, there has to be 2 + 1s. If this was 2 + 2 + times 2 is positive 4. But 2 times 1 is positive 2. Positive 2 minus negative 2 is 0. So that would be copper 1 sulfide. Just one more example. One that doesn't have oxide sulfide. So let's say CrCl3. Clearly, this is a chloride. Cr stands for chromium. But what is our charge on chromium? So we have to look. Chloride is -1 because it's group 7. If it looks like I don't have to look very hard or very long, it's because I know a lot of the common charges of these guys. So -1, because there's 3 of these, the total negative charge is -3. In order to cancel out with chromium, chromium must be +3. So that'd be chromium 3 chloride when we come to name that. Chromium 3 chloride. So that's what I mean when I say I have to look to the anion to determine the cation. If it's group 1, 2, or 3, silver or zinc, I don't have to look because I don't have to compare because they are always mixed together. Silver oxide, for example, if I'm going backwards, silver oxide, when I go to do that, silver is always +1. Oxygen is always 2-. What way am I going to combine these together to form a neutral compound? If that's 2- and that's +1, I'm going to have to double that up so that they cancel out. If I'm going to work my way one more with a transition metal. Let's say manganese 4, which is our IV oxide. So manganese +4, oxygen -2. What way do we get +4 and -2 to cancel out? I double my -2. So let's say MnO2 would be our manganese 4 oxide. So we should be able to go from name to formula or formula to name. That's one of our goals for this chapter. I want to take that quick aside before we go into the next level up. We will not get through all of this, but we will get a bit of the way into this. Okay. Polyatomic anions. Polyatomic ions in general. So most of these anions are an individual atom type, but some of them are going to be a combination of atoms. Most of these guys will be anions, but there's a couple cations, like 1 or 2. Some we'll just need to memorize the common name, but some, as we'll learn, will follow a pattern. Most common polyatomics will fit into the category of what's called an oxyanion. Breaking that down, oxy means oxygen, and then we anion. So some mixture of an element with an anion. We will learn most of the non-metal on oxyanions, But there are a few metal ones that we may see that you may have heard of. But SO4, 2 minus is sulfate. That's a common one. NO3, 1 minus is nitrate. NO2, 1 minus is nitrite. ClO4, 1 minus is perchlorate. We're going to deal with some perchlorate in lab for lab 2. MnO4, 1 minus is permanganate. We will deal with that at the end of the semester when we do a Beer's Law lab. But you'll notice ate and ite. We have some weird names. We have permanganate, perchlorate. Hopefully you recognize the manganese in the manganate. Hopefully you recognize the chlorine in the perchlorate. Nitrate, nitrite, you hopefully recognize the nitrogen. Sulfate, you recognize the sulfur. Most of these guys will have 2 or more structures containing a different amount of oxygens, but all of these structures will contain the same charge. So all nitrogen ones will be -1. All sulfur containing ones will be -2. All chlorine containing ones will be -1. And so on. All bromine ones will be -1. But I could have ClO4 1 minus, ClO3 1 minus, ClO2 1 minus, ClO1 1 minus. All like anywhere from 1 to 4 oxygens. And so I have to have a way to differentiate the naming of those 4 anions. Now, typically, if there's typically 2 structures, if there's any at all. And the one with the more oxygen will get an ATE ending. So instead of being an ide, instead of this being like chloride, we're going to call this sound like chlorate. If we have the less amount of oxygens, we're going to get the less one is going to be ITE, like chlorite. So that when we see nitrate and nitrite here, nitrate is the one with more oxygens. Nitrite would be the one with 1 less oxygen, so 3 to 2. Sulfate has 4 oxygens. If we lost one, we would get to sulfite. So SO3, 2 minus would be sulfite. We're going to probably go ahead and stop there because looking at this big thing is going to take us a little bit of time. So keep working on that, practice this. Be working on the homework. Please note there is some homework due tonight. So be doing that. And I will see you guys in lab, well, some of you in lab, and see the rest of you on Wednesday.